Hello, everybody. So my goal today is I'm going to fill you in on some of the product development going on at Ajax Therapeutics. And in doing so, I'll be making certain forward-looking statements. We're a public company, so please refer to our filings with SEC for more detailed information about the company. Now, I've got kind of an ambitious agenda here. I wanted to cover quite a bit of ground. So, and I'm not typically thinking of myself as a fast talker, but I'm going to try, okay? Because I want to race through a lot of stuff. And forgive me for starting out. You probably look at this and say, oh gosh, not another demographic slide. I only want to make one point about the aging U.S. population. You look at that inflection point, that's 2020, that's right where we're at. And the problem I just want to highlight is not only aging, but chronic degenerative disease. Did you guys know this? 80% of the healthcare costs of the United States, which is like, what, some people say $2.5 trillion a year, 80% is chronic disease. And aging is the largest source of chronic degenerative disease. And this is my point. Because the human body cannot regenerate itself after afflicted with trauma and chronic degenerative disease. You have myocardial ischemia, you lose heart muscle, it scars over, you don't grow heart muscle back. And the reason I'm mentioning that is the whole theme of my talk is making it grow back. Okay, so that's my point. So this is, as other speakers have pointed out, what's going on in aging research right now is just within the last hour, someone asked me, what do I expect to see in aging research? And I think it's rather dramatic, actually, what I'm expecting to see. Beyond what you can imagine, really. All right, so another thing I'm going to talk about is I'll be talking about, and you guys have heard about the dichotomy of the germline versus the soma. And this is an ongoing theme through all the slides I'll show you. So you know this, right? Where you are made from a lineage of cells that have been proliferating for billions of years. The cells that made you have no dead ancestors, right? Right? Think about it, right? So the cells that make up our body, the somatic cells, are the cells that have this bizarre thing called aging that lasts a few decades. All right, so in red here is the immortal germline, and then the cells which I'll be talking about that branch out to make somatic cells all have some common features. And you say, oh no, Mike, they're very different. You've got muscle cells, you've got bone cells, you've got retinal cells, all these. That's right, different kinds of differentiated cells make up our body. But they have some common features, one of which you know about, which is cell aging, the Hayflick phenomenon. If they proliferate, they can only proliferate for a finite number of doublings. Why is that automatically advancing? All right, so the first thing is we came up with this idea back in the Geron days of isolating what essentially are the germline cells, embryonic stem cells. These cells are at the very beginning of development, and we thought that they probably had telomerase and they were probably immortal. The only human cell, other than cancer cells, that are naturally immortal. And it turned out that that's exactly right. And of course, the beauty of these embryonic stem cells is that allows industrial scalability. Their replicative immortality allows you to do precise genetic engineering. You can make any kind of cell engineered any way, and they are all young and regenerative is one of the things I'm going to be talking about. So in this context I just described of 80% of our healthcare costs being directed to this previously unsolvable problem of chronic degenerative disease, pluripotent cells the platform allows regenerative medicine 1.0, which is the manufacture of young cells of any kind for regenerative therapies. All right. Just a little bit of context here. Again, I'll go quickly over this. This is a true platform technology that's revolutionary. It's like recombinant DNA, allowed you to make any protein, virtually any protein, industrially scalable, and that was the basis of Genentech and Amgen. Took some 20 years from basic discovery to commercialization, but when it hit commercialization, you guys know, right? Changed medicine forever, billion-dollar industry. Monoclonals the same way. Regenerative medicine 1.0 is now taking off. I got some of the deals here. My old company, Lineage, at the bottom, LCTX, just sold off one of its products, the retinal pigment epithelial cells, for age-related macular degeneration. Just one little application for $670 million to Roche Genentech. And the stem cell regenerative medicine thing is like any other biologic. You know, you can scale it up in a centralized facility, phrase product, send it out to point of care. It's like monoclonals, it's like recombinant proteins and so on. Now, let's talk about somatic cells. So, somatic cells that make up our body very early in development, like 2 weeks after the egg is fertilized, they say, oh, we're not going to proliferate forever. We're not going to be a germline cell. You remember the Woody Allen movie? There's a sperm wondering whether he's going to make it or not. They say, oh, you know, we're not going to be part of the immortal germline. We're going to be some part of the body that dies. Turn off telomerase, start the clock ticking. And I call that somatic restriction because you're restricting the immortal regenerative potential of the germline. Now, early on, evolutionary biologists figured out that probably what's going on is nature is doing that to help prevent cancer. It's called antagonistic pleiotropy. Nature's trading off something that helps you when you're young, but has a deleterious effect late in life. And we think that this is a classic example of this idea of antagonistic pleiotropy. What I'm showing you here in this graph, it's kind of busy and I don't have time to explain it all, but on the left, this is the expression of the telomerase catalytic component, the immortalizing enzyme, telomerase. And you can see on the far left, embryonic stem cells and their sister cell, iPS cells, have telomerase. They're an naturally immortal cell. The diverse embryonic progenitors are cells we made which are very primitive but somatic, and they've already turned off telomerase, even though they're very primitive. Diverse somatic cells, those are neurons and liver, all mortal. And then on the right are cancer cells. And cancer cells nearly universally have become immortal again. That's this antagonistic pleiotropy thing. So yin and yang, aging and cancer, right? I'm introducing this because it's going to mean something in future slides. Now, what I was interested in is showing you some slides. Why did my slides turn off? I'm assuming you guys are working on that. So, right? So, what I was interested in was what I just described, the switch to mortality, right? The cells undergo in our body, occurs really at the first stages of life, within a month after the egg is fertilized. Your cells switch to this mortal code. And are there other changes that are occurring in somatic cells, or is telomerase the only one? And if you guys can get those slides working, it'd be helpful. So I noticed in the scientific literature that early in development, human tissues like skin, let's take skin as an example. If you do a full thickness incision in the skin early in human development, the skin will naturally regenerate scarlessly. But then later in fetal development and adulthood, skin doesn't regenerate. It heals in a sense, but it scars. I'm going to try to back up here. There we go. And then, what the heck's going on, you guys? So, did you see the picture there before it went away? So there are animals in nature that where the developmental timeline is perturbed, it's changed. It's called heterochrony, or different clocking, or different timing. And an example you probably have heard of is the Mexican salamander. So you guys seen these animals? You cut their leg off and it just grows back. Now, they didn't evolve that way. They have mutations that have caused them to stop their development while they're still in that early regenerative mode. Like humans have, we have that same ability when the body is first forming. So there you can see the legs regenerating after amputation. I'm going to skip that because maybe that slide was the problem. And here I'm highlighting, people then studied, okay, when in mammals, when in humans, for instance, when is that switch occurring that's turning off a natural and profound regenerative potential? I can't overestimate how amazing this is. In the Mexican salamander, you can just go in and take a big chunk of their brain out, and it'll regenerate, and they'll regain neural tracts and learn to see again and learn to swallow again. Yet the stuff flies there on the throat in the meantime. But think about that. That is just amazing. Can you imagine the clinical impact would be if we, after a stroke, we could induce that kind of a regenerative effect to regenerate CNS function, or, of course, the list is endless. Remember my graph of the 80% of healthcare costs? So we thought this was really interesting, and perhaps in studying aging, everyone's comparing young and old cells. Maybe the switch is occurring earlier. Maybe the switch to the non-regenerative state, like telomerase, is a trade-off against cancer, and it's occurring very early, and it's been missed, okay? But even if it had nothing to do with aging, if we could learn about regeneration, of course, it's a very big thing. But if it had a fundamental role in aging and regeneration and cancer, then this is a really, really big idea. So back 2013 or so, this is just showing how different animals, where that switch occurs. So this is a picture from 2000 where we were seeing, can we reprogram cells back in terms of telomere length and developmental timing? Is it reversible? Everyone knew that through cloning, that development is reversible. The question is can we reset the clock of aging? In the year 2000, we published data on cell aging and telomere length. I won't go over it all. You guys maybe already know this. So we showed that it's completely reversible. The idea that Dolly was born old was it's never been reproduced. It was an N of 1. You know, if you look at the original paper, it was published in Nature, but it was N equals 1. It's been repeated many times. Nuclear transfer resets aging. So then, as you know, as this field evolved, the molecular regulatory factors like transcription factors and so on that are in the egg cell that act as a time machine to reprogram cells back to the beginning of life became known. There's a list of these genes. I'm showing you some of them there. And that was the birth of this thing called iPS cells, which many people now use instead of embryonic stem cells. I still like ES cells myself, preferred modality. But then, now can you see where I'm headed? Then the question arose, if what I told you was true, that there's a switch that's occurring later than telomerase at this embryonic fetal transition, so in humans it's like 8 weeks into development, can we use the power of these reprogramming genes to take cells back to that regenerative state? It's a clumsy technique. Clumsy meaning brutal, meaning, you know, it's like, if you want, I'm trying to think of a good analogy. If you want That's not a good way of saying it. Say if you want your child to turn around and hit him with a baseball bat, and that sounds awful. I mean, it's used too much force. If you want cells to go back to the regenerative state, I mean, pushing them with the force of these reprogramming factors that are designed to take them to pluripotency, that's brutal. And there's a huge risk, everyone believes, and I believe, for cancer. So, but as a first generation approach, let's try it. And you've heard some talks already. Turn is working in this and other companies. And we started working on this around 2013 and considering it being very important. And so that I call regenerative medicine 2.0. And it can work in parallel with cell-based therapy, but it's, as you know, Altos and others have raised massive amounts of money to enter this field. None of these other revolutions, platform revolutions, started out with such a strong start. And I think that's in part because some smart people know this is one of the bigger ideas that's ever been proposed. So what are we doing about it? So I just got a few minutes to quickly walk you through. I've got RegenMed 1.0 and 2.0 and cancer applications in the company. RegenMed 1.0, brown fat. What's brown fat? Here labeled in the human body, you see on the right there these black splotches. One's the heart, but the rest of them are brown fat. See the graph there that shows loss of BAT or brown adipose tissue with age, the loss of activity. It's thought to be a significant driver of metabolic imbalance in aging. So, we all have heard talks already about diet and type 2 diabetes. If you can cut or manage your diet or increase exercise, you can keep the body trim and actually reverse type 2 diabetes in patients. But a component that had been overlooked and only recently discovered, really, is the role of brown adipose tissue. This is sort of anti-fat. It takes lipid and sugar out of the blood, rather dramatically so, and generates heat. It's a major source of body heat, other than shivering and your furnace. And so the idea is simply, based on animal studies, if you added back this anti-fat or rebalanced brown adipose tissue in humans, can you do what has already been demonstrated in mice, which is reverse type 2 diabetes, not type 1, where you put in beta cells, but type 2 by putting in brown fat and simply cure the disease with cell transplantation. Well, the good news is we have a way we have a product called AGXBAT1 of making these cells industrially scalable and 100% pure. The latter is a major innovation. So on the left is brown fat tissue taken from a very young donor, and stained red is the marker for brown fat. And on the right is our product using a technology we call PureStem. And you see these cells are 100% pure, human, regenerative brown fat, industrially scalable. So we're a public company. So I can't really go beyond that, I guess, except I think in one of the slides I said that this product significantly improves glucose tolerance and metabolic dysfunction in animals. And that's as much as I'll say at the moment on this. So type 2 diabetes is a very, very large market. It's probably 10 times bigger than type 1 in terms of market because of prevalence. Type 2, about 10 times more people have type 2 than type 1. All right, so now I want to talk about this reprogramming thing because I've got limited time. You guys have seen all this news about people throwing money at this age reversal using reprogramming. So again, to refresh your memory, I said there's these multiple steps of somatic restriction. So don't just think about things that change late in life. They're occurring early in life. One, you turn off telomerase, the clock starts ticking, telomeres are shortening throughout your lifetime. to the early loss of regeneration, once the body's formed, in a sense, nature doesn't, I don't think nature is sentient, and some of you may think it is, but in a sense, nature's saying, you formed the body, you don't need to be able to form it again, right? So I'm turning that off. In the Mexican salamander, it's not turned off. And there's many other examples other than the salamander. What if we can turn it back on? How could we do it? And now my biggest point, really the point I wanted to make to you today, this is my main take-home message. How do we do it better than's been described to date? So, as I hinted at, 2013, we poured enormous resources into this. We said, look, this is really important. We want to know everything there is to know about this embryonic fetal transition, just like the regulation of telomerase and getting the telomerase gene. So what we did is we took, using embryonic stem cells, we made hundreds of different kinds of human somatic cells, and we took hundreds of adult counterparts. Okay? And we had now had an in vitro model to study what's different. How did cells lose regenerative potential? And since we had so many different kinds of cells, we could look for a universal mechanism for all somatic cells, right? Like if there was one. We didn't know that there was one until we looked. And like telomerase. We wanted to own this thing. So I often show this gene. It's just a marker. It's an important gene. It's a marker, but it's a beautiful marker, and that's why I show it. This is a gene called COX71, and it's a supercharger for oxidative phosphorylation. Let me just say that much. And on the left, this is gene expression. On the left, you can see embryonic stem cells don't express it, and these embryonic pre-EFT cells, even though they're differentiated, they don't express it. And then all these adult cells do, okay? So this is an example of a switch that's occurred throughout the body when regeneration turns off. And then you notice it's missing in a whole bunch of cancer cells, like telomerase. So it fit our criteria. Here is how this is, by the way, microarray data, so the little bit of signal you see in the ES cells is actually zero. It's background signal. And can you see how during the embryonic fetal transition, and this is skin, right at the 8 weeks, when regeneration's turning off, remember I showed you the mouse and rat when it turns off, and in human, this gene starts coming up in expression. And there are others. These are the heterochrony genes that Gary Ruvkin described, Lin28, for example. And here is Lin28 on a bit in our progenitors, screamingly high in pluripotent cells, and then reappearing in cancers, antagonistic pleiotropy. So how can we we've got dozens and dozens of pathways and genes we've identified here. I'm not disclosing it all. I'm not telling you about it all. But now let's talk about reprogramming. How do we induce the regenerative state? Well, one would be to use these reprogramming factors transiently, like Lin28B. By the way, here's a proof of concept. This is the African spiny mouse. Yank its skin off, all the way down to muscle. 60% of it, let's say, and they'll completely regenerate scarlessly, hair and all, everything. And look at Lin28 expression in acamese versus normal mice. So one approach to do this better and safer is to do segmental reprogramming. So don't hit the cells with these global reprogramming factors like Yamanaka factors, but just use the genes necessary to do reprogramming. And here we have mice where we look at hair regeneration by restoring COX71 and Lin28, the two genes I showed you, back to the embryonic state, and it had an explosive effect on hair regeneration. You can see the bottom where we have embryonic patterns of both. Actually, that's Lin28A. Or we can find another way to do the global reprogramming. Here is global reprogramming. This is what we call partial reprogramming. This is Aloha's paper. And there is COX7A1. And you can see that within just a few days, like 6, 7 days, COX7A1 goes back down to embryonic levels. This is partly justification for what was some of the other slides you saw earlier in the sessions, that transient expression of these factors can restore cells back to a regenerative state. Now, so how could we, but because the flip side of the coin is cancer, and like telomerase, restoring this regenerative state could lower defenses against cancer. And as one speaker pointed out, I think it was Turn, animal models, we're not seeing cancers in partial reprogramming. But nevertheless, FDA is going to be all over this. How do we help prevent the risk of cancer? Here's an idea we filed patents on called developmentally regulated induced tissue regeneration is our word for partial reprogramming. Use the COX7A1 promoter. Remember I just showed you? It turns on when cells are starting to turn off regeneration. Have it drive the reprogramming factors so that when cells are back just to where you want them, not back to pluripotency, back to the regenerative state, COX7A1 no longer is an active promoter, the genes are no longer expressed. We call that developmentally regulated ITR. All right, I just got 1 minute and 46 seconds. It's cancer, my last point. We all heard about the Horvath clock and methylated changes with age. Here is, circled in red, is the methylation of the genome at the COX7A1 gene as an example. The top two are embryonic, the next two are adult, and then the rest of them, a bunch of them, are cancer cells corresponding to normals. And you can see cancer cells are in the embryonic signature. And what we've learned is, for those of you that are interested in cancer, this is opening an entire unexplored new territory on cancer that's pan-cancer. Did you hear what I said? Pan-cancer. Like these phenomena about regeneration are true for endothelium and muscle and bone and cartilage. These cancer things we've discovered are pan-cancer. Generally speaking, cancer cells have reverted back to this embryonic signature, regenerative state, but some are in the adult state, and counterintuitively, for those of you who know cancer research, well, you see how I've got cancer stem cells marked out? The supposed cancer stem cell that scientists try to understand, because it's chemo-resistant, are the adult-like cells. They have it backwards. Oh my gosh. It opens all kinds of new opportunities for therapeutics. And the one that we're quite excited about is we believe in a pan-cancer therapeutic strategy based on this to target embryonic specific antigens and using promoters to specifically target and then lyse cancer cells. I wish I had more time to talk about it. So what I described really quickly is this platform, Regenerative Medicine 1.0 and 2.0, and then some products that come from it that could have a big impact on metabolic disease in the case of BAT1, but regeneration and aging in the case of skin, which we call Renolon, and the cancer product we call Epro. So there are things we can learn from the immortal germline. There are now in vitro models, which I described, like all these pluripotent stem cell-derived cells that allow us to model in the laboratory, like the Hayflick model allowed us to understand cell senescence. These cells allow us to understand this other transition, which is the embryonic fetal transition, and we believe it's opened the door now to precise reprogramming, not just a rather brutal approach to reprogramming, but precise reprogramming that potentially will allow us to have a product approved by FDA because we believe we can demonstrate that we can precisely regulate this process without significantly increasing the risk of cancer.